video, we're going to develop the logistic model. The logistic model depends on this differential equation to our right. Before we look at that more challenging differential equation, let's look at left. And this is a first order differential equation. First order differential equation. First order meaning the derivative dy dx, which is y prime. The derivative depends on the amount of y changes with respect to x. Depends on how much y there is. First order meaning y to the power of 1. So to solve these, we know that we split the y's and the x's. So we have 2y over y equals k x. And then we integrate. So on the left-hand side, we get ln of y, and on the right-hand side, kx plus c. I'm going to isolate for y, so we raise both sides, e to both sides, so e to the, and we're left with y equals e to the kx plus c. Using what we know about exponents, we can write this as y equals e to the c times e to the kx. And now what we're going to do is we're going to look at what is this value. Well, when x is 0, we're going to have our initial y amount. So when x is 0, y is our initial y amount. So plugging those 2 points in, we get y naught for y equals e to the c times e to the k 0. And we know that anything to the 0th power is just 1. So that shows us that e to the c is our initial y value. So from this first order differential equation, we get y equals our initial y amount, e to the kx. An exponential equation, which the idea of the differential equation says our rate of growth, so our derivative, dy dx, depends on a proportionality constant times how much y we have. In other words, the more y, the more it's going to grow. Now, oftentimes misused, we say that populations grow exponentially. But it's impossible for a population to actually grow exponentially. Instead, usually the population will grow exponentially for a little bit, and then it will taper out because there's some limiting amount that it can be. So that brings up the need for the logistic model. The logistic model, which is shown here, says that our derivative, dy dx, depends on y, and I'm going to expand this, times a y squared over L. And this idea is really important right here. And this is saying that for when y is much smaller than L, that kind of goes away, and we're left with just exponential. But when y gets bigger than L, when y approaches L, now all of a sudden we have this negative dy dx. This negative is going to slow growth. So as y approaches L, the growth slows and eventually almost stops. So the key difference between the logistic model and the first order differential is that there's this minus here. So what we want to do is we want to take this equation and expand it. We want to solve that differential equation. So to solve this, we need to use differential equation, solving a differential equation, so that we can develop the logistic model. Okay, so what we do, we say this is dy dx, and now I'm going to write the right-hand side as ky over L, and then that lets, in parentheses, L minus y. So essentially, like I factored out 1 over L. Next thing we do, we're going to move everything with a y over everything with an x to the other side. So we're going to take this over to the other side. And this is going to go there, that's going to go there, and what we get left with is L dy over y, L minus y, equals k dx. Well, now the step is to integrate. So we integrate. The left-hand side, or the right-hand side is going to integrate really nicely. We get k x plus c. But the left-hand side, we're going to need to use partial fractions. So we're going to have to do some work on this piece. We know that we could write that as a over y plus b over L minus y, and that's going to have to equal L over y, L minus y. And now what we need to do is expand these. So we have a L minus y plus b y must equal L. Looking just at the numerator, so this is a review of doing partial fractions, which was for 10.3. So we're going to look at when when y equals 0. So when y equals 0, this piece is going to go away, and we get a times L minus y must, and y is 0, so 0 must equal L. So we get AL equals L. So in other words, we know that A must equal 1. Now we look at when, so that was when this was 0. Now we need to look at that being 0, so we look when y equals L. And when y equals L, the left-hand side will be 0, this will be 0. So we're just going to get b times L equals L. So b must be 1. So therefore, we can rewrite this fraction as a partial fraction, the integral of a over y, so 1 over y, plus the integral of b over L minus y, so b over L minus y, and that's coming from taking these points, a is 1, b is 1, and plugging it back into our partial fraction. And now, and this equals kx plus c. Now let's move this whole thing onto a new page so it's a little bit fresher. All right, to do this integration, we're just going to get a bunch of ln. So this is going to become ln of y plus 1 over L minus y. We need to remember that L is a constant, so this will be plus negative ln of L minus y. That equals kx plus c. Combining logs, we get ln of y over L minus y equals kx plus c. And now we're just doing some rearranging, so this works out nicely. But this is, as far as you're concerned, this is just a nice review of some log rules. We can this negative. We're just multiplying both sides by negative 1. Well, multiplying by this negative in front on the left-hand side, that's negative 1. Using the exponent rule, we can write that as ln of y over L minus y to the negative 1. You're bringing that power up, and that equals negative kx minus c. And then using what we know about a negative exponent, this is ln of L minus y over y equals negative kx minus c. Then we're going to raise both sides to the e. So and we get L minus y over y equals e to the negative kx minus c. We're getting closer now. We can split my left-hand side. We can split that as e to the negative c times e to the negative kx. And doing a little bit of math, which we're going to skip for time being, but when x equals 0, y must be its initial amount. So if I were to plug these givens into here, we can then find out the value of this, and that equals L minus y naught over y naught e to the negative kx. And again, this value here comes from plugging our initial value where x equals 0, y must be its initial y value, into this equation just to solve for our constant. But from now on, let's call this value a. Okay, so continuing on, clearly this is a challenging integration problem. We have L minus y over y equals a e to the negative kx. Now we just need to solve for y. So solving for y, let's look at this fraction, and we're going to do that on another page. So we have L minus y over y equals a e to the negative kx, and well, we can split this fraction. L over y minus y over y equals a e to the negative kx. Y over y is just 1, so we have L over y minus 1, a e to the negative kx. Now let's get this y here all by itself. First thing we're going to do is move this 1 over. And now we can essentially cross multiply and multiply both sides by y, and divide both sides by a e to the negative kx plus 1. And what we're left with is that y equals L over, switching the denominator 1, plus a e to the negative kx. And this is our logistic model where a equals L minus y naught over y naught. And therefore we get this relationship that if we have the following differential equation, that this is the solution.